Right, guys. Well, so we're going to get started with our chapter one with section 1.1 on systems of linear equations material you have done in the past in your algebra courses. All right. However, we may introduce other mechanics here, other notation, or more formal definition. All right. Okay, so number one, what's a linear equation? A linear equation in n variables, even though you learn a linear equation like y equals mx plus b, that's a linear equation in two variables. But then there are more variables that we can use like a linear equation in three variables, which is the equation of a plane. Those of you who have taken Calc 3 or are going to take it right after this class, we're going to look at that, right? Okay, but it turns out that we can add as many variables as we want, all right? So how do we distinguish a linear equation? All variables, okay, are raised to the first power here. If you have something like an x squared, x cubed, a radical, a trig, an exponent, that's no longer a linear equation. All right, it has to be a coefficient, a numerical coefficient, and see how x1, x2, etc. They are all raised to the invisible one power. Okay. All right. So like, first example, how about we determine whether these equations are linear? So, letter A, yes or no? I mean, numerical coefficients, all variables appear to the first power, so why not? I don't see why not, all right? Letter B, linear or non-linear? No, yes, I see a combination of yeses and nos. So, why is that a linear equation, however? Okay, so I think the cosine pi right here might be the weird part of the problem. Be careful. It's not the same to say cosine of pi x, which is a nonlinear function. This is a trigonometric function. This is not equal to cosine of pi times x. This is x to the first power, the cosine pi, which is what's that, negative one, right? Negative one. Well, negative one times x to the first, it's still linear. So, yes. And letter C? No, why not? So in this case, we have we have x to the first and y to the first. However, these two are multiplying overall, giving us a same power that um, get classified as a linear equation. All right. Okay, guys, you are used to solve linear equations like when you have something like 3x plus 1 equals to 0. What do you do? Yes? Yes. Yeah, totally. Yeah. Thank you. Thank you. Okay, so we are used to solve linear equations. I mean, what do we do? Um, subtract 1 on both sides. 3x equals to negative 1, and x equals to negative 1/3, right? Or sometimes when we have an equation, a linear equation in three variables, like x plus y equals to 1, for instance, right? And well, in many cases, we are asked to solve for y or solve for x depending on our purpose. Do we want to graph this equation? Do we want to parameterize that equation about? Well, it depends. All right. So like y equals to x, what is that? X, no, negative x plus 1, right? Oh, come on, I can't write today. Negative x plus 1. So that really means x equals simply x and y is negative x plus 1. So everything is in terms of x, right? Okay, but what if we had more variables like the equation of a plane? You guys may have worked with the equation of a plane that is a linear equation in three variables. And more than likely, we use to solve for a z to get the base of a solid, to evaluate a double or a triple integral, or to do the peekaboo for graphing that plane. All right, but what are we going to do this time? It turns out that we can solve a linear equation, one equation, multiple variables in parametric form. We're going to define what we call a parametric solution and free variables. All right, for instance, let's have a look. Let's see how we do this. Okay, here are the steps. Okay, so choose the variable or the variables that occur the last in the equation. Those are going to be our free variables. It doesn't have to be the last ones. You can choose one variable to be the basic, remaining ones to be the free variable. But at least you need to take one as the basic. So that's the variable we're going to solve for, right? What do we do? Okay, assign a parameter variable to the free variables, all right? These free variables are usually labeled with letter R, letter S, and letter T. I'm pretty sure you have used letter T before, right? You've used it a lot. We're going to use more variables here, okay? What else we're going to do here? Solve for the first variable, that is the first, really the basic variable. And then replace the free variable with their parameters. And then we can find a parametric solution by choosing values for the parameters, all right? Okay, here we go. One example. So finding the solution to this linear equation. Well, you can make your free variable the one whatever variable you want, okay? Favorite variable. But usually, again, we we make the first to be the basic, and we solve for the other ones, the turning them into the what's it called, the free variable. So for letter A, 7x1 minus 5 over 9 x2 equals -1. I'm going to solve for x1. 7x1 equals to 5 over 9 x2 minus 1. Okay. And then I'm going to divide both sides by, or rather, I'm going to multiply by 1/7 instead. Okay. I think it's better than the division because I don't want to divide the fraction by a number. That's kind of weird. All right. And then that's x1 equals to 5 over 9 times 7 is that a 63. X2 and minus 1 over 7. Right? So, so that is our solution. Okay. So in this case, this is our, again, basic variable. And this is our free variable. Okay. So what are we going to do? Yes.
Did the did the how did the -5 over 9 become a positive?
Oh, because it was negative, we move it to the right-hand side as positive with the opposite sign. Yep. And what do we do next? Okay, so what do we do? Let the free variable x2 equals the parameter t. Okay. So what do we get? Can we make this to even looking better? Okay. So that is okay. We're gonna substitute x1 equals to 5 over 63 t minus 1 over 7, right? Minus 1 over 7. Okay, so we need to express our solution as an order pair. Like when we solve a system of linear equations with two equations and two unknowns, we usually write our solutions as order pairs. And order pairs typically xy, but in this case we're not using xy, we're using x1 and x2. Well, what's x1? x1 equals to 5 over 63 t minus 1/7, comma, x2, which is t. That's the parameter. And we'll always say here that t belongs to the set of all real numbers, right? Any real number. Okay. So that is one example. Okay. Let's have a look at another example, letter B. Okay, letter B, an example number. Oh, I ran out of space right here. Let me make this a bit smaller. Okay. Thought I was going to have enough space right here. Okay. All right. So for letter B, okay, letter B, I'm going to take 6x minus 8y plus 10z equals to 3. Again, you have your choice to let x or y or z the basic variable and the remaining ones uh, the free variables. But again, typically the first one we see, or the first one we see, which is x, or the first one in alphabetic order, or the first one in the subscript denomination, it's the one that we take as our basic. Uh, so 6x equals to 8y minus 10z equals to, plus 3. All right. In this case, how many free variables do we have this time? Two. So we're going to use two denominations here or two parameterizations, really. So in this case, oh, wait. Let me solve for x. X equals to 8 over 6. Is that 4 thirds? And 10 over 6. Is that negative 5 thirds? And then 3 over 6. Is that plus 1 half, right? Okay, so at this point, we're going to set, or rather let y equals to it doesn't matter which variable do you assign to the free variables. The order doesn't matter really. Y equals to s and z equals to t. Okay, let's do that. Substitute into the equation. X equals to 4 thirds y minus 5 thirds z plus 1 half. Oh, wait, what the hell am I doing? Yeah, S and T, right? S and T. Okay, that S looks like a 5. Okay, there we go. Much better. Yeah, sometimes, sometimes my S's looks like 5 or diff or vice versa. V's like X's. So if something is not clear, feel free to raise your hand and let me know, okay? So that being said, okay, as an order triple, X, Y, Z, that equals to, okay, what's X? X is in terms of S and T. What was Y? Isn't that S? And what about Z? That equals to T. Okay. So that's how we solve linear equations with more than one variable using parameters, right? That's something you may not have done before. So, well, anyway. So that's it. Okay, so systems of linear equations. So now let's make more equations, even though more unknowns, but now with more equations. Okay, and this is really the general form of a system of equations, which, by the way, it should have these curly braces here. That's like what makes it look like a system of equations, what ties together the equations, right? Okay, um, so it's just a bunch of linear equations for which we may have the same amount of variables as equations, or maybe more variables than equations, or maybe more equations than variables. There are many cases we can run into. So, and that actually depends on the applications, which is the end of the chapter, to like traffic networks, to like balancing chemical equations. What else are we going to do in that chapter? We will look at interpolation, a polynomial interpolation, when you have a collection of points and you want to find, like in linear, no, in statistics, you find the line of best fit, but well, it turns out we can find the parabola that best fits a set of points, the cubic that best fits a set of points, or your favorite degree of a polynomial. You'll see. Okay. So number one, what does it mean to solve a system of equations? This is basic algebra, right? Two equations with two unknowns. Those are two linear equations, two lines. And there are three possible case scenarios. Number one, geometrically, these lines may intersect, may overlap, or may never intersect. That means unique solution, infinitely many solutions because they're overlapping at infinitely many points on the graph. They never touch. They never intersect. That means no solution, no point in common. Because that's what the solution of a system of equation really represents. What's the point in common, the point in intersection between two curves in general, but in this case between lines. Let's put our 3D glasses on here and see what does it mean to solve a system of linear equations with three equations and three unknowns. All right, that green picture here represents the unique solution when we have the three planes intersecting at only one point. The following three cases with the pink color, we have the planes well intersecting at infinitely many points. So we may have the three planes intersecting but on a line. We may have three intersecting planes, right? Three overlapping planes or two overlapping planes and then intersecting with another plane at an end. And it doesn't matter no matter what, these two cases intersect on a line. And these guys right here are really the same plane. That's all that is, right? Case number three, no solution. Well, three planes that never intersect, all right? Just like the two parallel lines, well, here, three parallel planes. No solution here, despite there is a line of intersection here. There's another line of intersection here. However, that line, because that line of intersection is not common to the three planes, that means no solution. Over here, we have the same case scenario. We have three lines of intersection. There's one here, another one there, and then there's another one, an invisible one right here. Three different lines, but it's not common to the three planes, no solution. Or otherwise, what do we have? Two planes overlapping, having intersecting at infinitely many points. Okay, that looks promising. However, there's a third plane that does not intersect to those planes. That wins, right? We go with it. No solution. Intersection, no solution. All right, what's next? So let's solve some systems of equations, okay? Um, what can we do to solve a system of equations? And this refers to what you learned back in pre-calculus or college algebra or even in high school to solve systems of equation. We can interchange two equations, multiply an equation by a non-zero constant, or we're going to call it scalar later, and add a multiple of an equation to another. We're going to do this again in the following section, in the next section, using matrices. But in the meantime, we're going to do with the equations, okay? All right. So, let's solve the system of equation here. So the idea is to eliminate the x below the x's below that x, and then eliminate the y below, and then do what we call a back substitution. I'll show you how that works. Okay. So let me call this 1, 2, and 3. Okay, so I would like to eliminate the x in the first term of the second equation and the 2x in the first term of the third equation. Okay, so this is what we're going to do. We will, how about just combining the two equations together, like equation 1 plus equation 2, and replace that with a new equation 2. Okay, if we do the operations on the side, I'm going to do x minus 2y plus 3z equals to 9, and then minus x plus 3y plus 0 equals to negative 4. If we combine these two together, what do we get? The x's cancel, 3y minus 2y, is that just y? And then 3z plus 0, that's just 3z. And then 9 minus 4, is that equal to 5? So that's going to be our new equation 2. And at the same time, guys, we can do, okay, let me actually make this longer, okay? How could we eliminate these two x here? How about multiplying the first equation by negative 2 and adding it to the third equation? That would actually cancel the two x's. Do you see what's going on? Okay. So let me do negative 2 times 1 plus 3 to come up with a new 3. Okay. So let me do it on the other side right here. So 2 times x minus 2y plus 3z equals to 9. Also, that times 2. Oh, actually, negative 2, right? Negative. Okay, negative 2. All right. And well, what are we going to do here? What are we going to do from here? Okay, so add. What is that? We're going to add 2x minus 5y plus 5z equals to 17, right? Okay. All right, guys, I don't want to rewrite the whole thing. How about, okay, let's do the operations on the side. Negative 2x plus 2x, don't they cancel each other? Okay, negative 2 times negative 2y, is that 4y? Minus 5y, is that negative y? And then negative 2 times 3z, is that negative 6z? Negative 6z plus 5z, is that negative z? And then 9 times negative 2 plus 17, is that negative 2? Wait a minute. No, it's negative 18, right? So that's a negative 1, right? And that's going to be our new 3. So I'm going to rewrite the system the following way. Okay, so that is the first equation remains the same, x minus 2y plus 3z equals to 9. And then, okay, the new second equation becomes y plus 3z equals negative 4. Oh, wait, equals to 5. And negative y minus z equals negative 1. So we just got rid of the x. Well, um, let's get rid of this y. Actually, it's fairly easy to do this because all it takes is to add equation 2 with equation 3. The third equation, the y in the third equation, right? So let me denote that. So 2 plus 3 to obtain a new 3. Okay, actually, I should have used blue over here. Turn this into blue because I'm using a different color for the side operations, right? Okay, all right. So what is this? Okay, so let me do that operation on the side. So that'll be y plus 3z equals to 5. Negative y minus z equals to negative 1. Adding these two together, 0, 2, z, and 4. Okay? So I'm going to rewrite the system back to blue. That'll be x minus 2y plus 3z equals 9. Y plus 3z equals 5. And 2z equals to 4. Okay, we're essentially done with equation operations. What do we have? We have a system in triangular form. So you see this? Do you see the shape of the triangle here? So we have one x and zeros below. We have two y's and one zero below, and all and the entire, so to speak, column with z. In this case, I'm going to use back substitution because, okay, check this out. I can set 2z equals to 4 and divide both sides by 2. That is z equals to, what is that, 2, right? Now we know z. What does that mean? We can go back to the second equation, all right, and find y because we already know z, don't we? All right, so let's see. So y plus 3 uh, 3 times, what is that? 3 times 2 equals to 5. That is y plus 6 equals to 5. And y equals to, what is that? Negative 1? Okay, negative 1. Now that we know the values of z and y, we can easily go to the first equation and find x. Okay, so x minus 2 times y, which is negative 1, be careful, plus 3 times z, which is 2. And that equals to 9. So what is that equal to? Uh, x minus plus rather 2. 3 times 2, is that equal to 6? Equals to 9. That is actually x plus 8 equals to 9. And x equals to 1. All right. Solution, final answer, the order triple x, y, z, that equals x equals to 1, y equals to negative 1, and z equal to 2. Okay? So that is our first solution to a system. And I really don't want to spend a lot of time. I mean, you have done a lot of this in the past. However, I think I'm going to do one more, I believe. I want to do, yeah, let me do this one. Okay. All right. Okay, so this is a no, this is not of me missing terms. No, that's actually the equation written by on purpose in this one. Because the purpose of this exercise is to use other operations. Because what do we want? We want a triangular system of equations, right? So that you want the top left corner, right? Any ideas what to do to get that? What was that? 0x, or how about interchanging these two equations? Okay, how do we denote this? Check this out. To denote the interchange of two equations, we do one double-sided arrow here with a two. That's how we denote interchange of equations. Okay, so what do we do next? So that becomes x minus 3z equals to negative 1, y minus z equals 0, and negative x plus 3y equals to 1. Okay? Okay, does that look better? Does that look more like a triangular matrix? Not matrix. Can I have it again? No, like more like a triangular system. Okay, but we need to get rid of this negative x, right? It should be nothing too crazy to do because all it takes is simply adding 1 plus 3 to obtain a new 3. Okay? All right, well, let me do the operation on the side. X minus 3z equals negative 1, negative x plus 3y equals 1. That's 0, 3y minus 3z equals to, what is that? 0, isn't it? Isn't that 0? Okay, which actually, you know what? I'm going to reduce this to, because everything is divisible by 3, agree? And there's a 0 on the right-hand side, so why not? Y minus z equals to 0. So I'm going to go back to the system and write it. X minus 3z equals negative 1. And then what's next? Y minus z equals to 0. And then, oh, another y minus z equals to 0. Okay. So what are we going to do about this one? Okay, so do you see how we can actually multiply the opposite? Because to cancel this y, we would need to multiply the opposite in sign of 2 and add it to 3 to obtain a new 3. And you see what's going to happen? X minus 3z equals to negative 1. All right. Okay, I'm going to write y minus z, and then let me do the operation on the side. Okay, so that is negative y minus z equals to 0. I mean, I'm not going to write the 0 by negative. I think it's very redundant to do. Y minus z equals to 0. Okay, negative y plus y, don't they cancel out? Negative times negative equals positive. Z minus z, don't they cancel out as well? So what do we get? 0 equals to 0, isn't it? Okay, all right. So, okay, but what is this going to mean anyway? Okay, let me write. I know this is silly to write, you know? This is so silly to write 0 equals to 0. That's technically our new third equation, but we have a little problem. We don't have that letter that describes that variable. All right. So whenever we have what we call a logical statement, right? 0 equals 0, right? Unless you get something like 0 equals to 5 or something. Yes. No, there's no reason for that. Uh huh. Thank you. Yeah, has to be, the zero has to be there. Thank you, thank you. So that means whenever zero like this, where say a z or a y or an x should be, that's your free variable. All right? Let me write that down. Means z is free. So let let z equals to t, right? That's going to be our parameter, right? And because check this out. Do you see y minus z and y minus c? Those are essentially the same equation. Those are two planes in space that are overlapping with each other, right? And then we have another plane forming whatever angle, doesn't really matter, intersecting at infinitely many points of the form that we're going to show parametrically here. Okay, so that'll be y minus z equals to 0, which means y equals to z, which means y equals to t. And on the other hand, x minus 3, z equals to negative 1, x equals to 3z minus 1, x equals to 3t minus 1. So we're done solving the system, except that we need to write it in order triple, in this case, form, right? X, Y, Z. The separable order triples where x is 3t minus 1, y equals to t, and z is also t, right? Final answer, right? Final answer. Okay, I believe this is the end of the section, isn't it?